Hello again. This is Math 2232 coming to you from the College of DuPage. The title of this lecture is The Ratio Test. As always, please be attentive while watching this video. By way of introduction, the ratio test can be used on any series, but unfortunately will not always yield a conclusive answer as to whether a series will converge absolutely or diverge. A proof of the ratio test is given in this lecture. But we're going to now take looks at this test that can be used to see if a series is absolutely convergent or not. Recall that if a series is absolutely convergent, then we will also know that it's convergent, and so we'll often use the ratio test to simply determine the convergence of a series. Before proceeding with examples of the test, it's useful for us to do a quick reminder about factorials. This test will be particularly useful, as you will see, for series that contain factorials, and we'll run into those a lot in the applications. So we want to make sure we can deal with them before we do an application with them. So recall, if n is an integer, such that n is greater than or equal to 0, then the factorial is defined as, if n is bigger than or equal to 1, n factorial is 1 times 2 times 3 times ... times n minus 2, n minus 1 times n. And 0 factorial is defined to be 1. So if we compute a few of these, we see that 1 factorial is 1, 2 factorial is 2 times 1 or 2, 3 factorial is 3 times 2 times 1 or 6, 4 factorial is 4 times 3 times 2 times 1, which is 24, and 5 factorial is 5 times 4 times 3 times 2 times 1, which is 120. So you see these things grow really, really fast. Moreover, in the calculations, in general, we can always strip out factors from a factorial in the following way. So n factorial is 1 times 2 times 3, ... and then we go up and we have n minus the whole of k plus 1, and then this is n minus k ... It goes up to n minus 2, n minus 1 times n. Or what we can do is say, well, 1 times 2 times 3 all the way up to n minus the whole of k plus 1 is really n minus k factorial. And this is the same thing as, if I distribute the minus sign, n minus k minus 1 factorial. So sometimes you have to do calculations like that. Also, when dealing with factorials, we need to be very careful about parentheses. For example, 2n whole factorial does not equal 2 times n factorial, because 2n whole factorial is 2n times 2n minus 1 times 2n minus 2 ... all the way down to 1. Whereas 2 times n factorial is 2 on the outside, and then it is 1 times 2 times 3 all the way up to n. These two numbers are not equal. This is often one of the more common mistakes students make, is to assume something like this, so be very careful. So now let's tell you what the ratio test is. All right, so the ratio test is quoted as follows. Suppose we have an infinite series, summation of a sub n. And if we define L to be the limit as n goes to infinity of the absolute value of a sub n plus 1 over a sub n, then if L is less than 1, the series is absolutely convergent, and hence it's also convergent. If L is bigger than 1, the series is divergent. And if L equal 1, the series may be divergent, conditionally convergent, or absolutely convergent. You just don't know. And a proof of this follows at the end of the section. And generally, here's what the proof does. We're trying to say this is the ratio of an plus 1 to an, which in a geometric series would be r. So you see, if r was less than 1, and we're saying eventually it becomes like a geometric series, that's where you get the absolute convergence and so on and so forth. If r is greater than 1, you know, and I know it's L here, but eventually if the series looks like a divergent geometric series, then it will be divergent. And if L equals 1, And this is where it becomes a little bit different. The geometric series for r equal 1 diverges, but here the series may, since you're taking the limit, may be divergent, conditionally convergent, or absolutely convergent. So we take this series, we form this ratio, and then we make a conclusion. But there are calculations involved in this limit. Again, we'll do a proof later on. You should notice that in the case of L equal 1, the ratio test really doesn't give you a conclusion, and you'll have to use a different test to determine the convergence of the series. Also, it's worth noting that the absolute value bars in the definition of L, these absolute value bars, are absolutely required. If they're not there, they will be impossible for us to get a correct answer. We'll look at an example of this. Okay, so here's the first one again. I encourage you to do these things either now or as a practice problem, or maybe both later. Determine if the following series is convergent or divergent. And this is the summation n equal 1 to infinity. This is minus 10 whole to the n. This is 4 to the 2n plus 1 times n plus 1. So that's pretty complicated stuff. And so what we'll do is we'll use the ratio test on this. So the first step is for us to figure out what is a sub n. So a sub n is just what this term is, so I just repeat it here. It's minus 10 whole to the n divided by 4 to the 2n plus 1 times n plus 1. But then we also have to know what n plus 1 is. So what we're going to do is we're substitute n plus 1 for everywhere. So this is going to be minus 10 to the exponent n plus 1. This is going to be 4. That is going to be 2 times, I'm going to put n plus 1 in there in parentheses, plus 1. And this is going to be n plus 1 plus 1. So that's what we'll get for a n plus 1. And this is what I said. Now you can simplify this a little bit because n plus 1 is n plus 2. And if I simplify this, I expand the 2 and collect terms, get 4 to the 2n plus 3. So this is what a n plus 1 is. Make sure you follow this calculation. And now we are going to calculate L. So L is the limit as n goes to infinity of the absolute value of a n plus 1. And it's really divided by this, but we're going to do 1 over this. And that means we're going to be taking the reciprocal of a sub n. Okay, so taking this times the reciprocal of a sub n, a lot of times it's easier. Students like to do that. Okay, so L is, and the absolute value is going to be important because that means we don't care if this is positive or negative. So what we're going to do, this is 10 to the n plus 1, but this is now being divided by minus 10 to the n. So we get minus 10 when we look at those. Here I have 4 to the 2n plus 1 divided by 4 to the 2n plus 3. That's going to be 4 squared in the denominator. And here I have n plus 1 over n plus 2. Now when I take the absolute value, and I've got, so the absolute value of minus 10 is 10, and 4 squared is 16. So this is going to be 10 over 16, and I pull that through the limit, and then I'm taking the limit as n goes to infinity of n plus 1 over n plus 2. Well, we've done enough of this so we know that this is, and that's actually in lowest terms, that's 5 over 8, but that is definitely less than 1. So since L is less than 1, we know by the ratio test this series converges absolutely, and hence it converges. Here's another problem for us to consider. Determine if the following series is convergent or divergent. Again, I probably won't ask the question this way. I'll ask you maybe, oh, what's L or something like that. But this one anyway is the summation n equals 0 to infinity. This is n factorial over 5 to the n. Now both of these grow very fast. 5 to the n goes very fast, and n factorial grows very fast. So it's kind of a race to see what's going on. Again, this is a great problem for you to practice. Now that we've worked out the detail, we can just go ahead and do this. So this is going to be a n plus 1. Make sure you see where that comes from. For this is the limit. As n goes to infinity, this is n plus 1 factorial over 5 to the n plus 1. And then I'm dividing this by n factorial over 5 to the n, but when I divide by that, that's multiplying by the reciprocal, so it's 5 to the n over n factorial. So now I have n plus 1 factorial. I have just a 5 because it's 5 to the n over 5 to the n plus 1, and this is n factorial. And this is the limit as n goes to infinity. But now let's see what happens when I look at n plus 1 factorial and n factorial. Well, n plus 1 factorial is n plus 1 times n factorial. So these n factorials cancel out. And so this is the limit as n tends to infinity of n plus 1 over 5. Well, that's infinity bigger than 1, so we know by the ratio test this series diverges. Here's another example. Determine if the following series is convergent or divergent. And this one you have the summation from n equal 2 to infinity. This is n squared over 2n minus 1 whole factorial. Okay, so, and again, as it says here, we need to be careful with the factorials. And again, this is a good practice problem. So L is going to be equal to the limit as n goes to infinity of a n plus 1. So I'm going to get n plus 1 squared over, this is 2, times n plus 1 minus 1 whole factorial. And then I put a sub n, but I invert it, I divide by it, but that's multiplying by the reciprocal. So this is 2n minus 1 whole factorial. And then this is n squared. Okay, so we'll continue doing work. Now here we do some arithmetic inside the parentheses, and we conclude that this is 2n plus 2 minus 1 is 2n plus 1 whole factorial, and this is 2n minus 1 factorial. So whenever I cancel this with this, I'm going to get 2n, well, I'm writing what this one is. This is 2n plus 1 times 2n minus 1. This is 2n minus 1 factorial, so I cancel this with that. And then I have n plus 1 squared over n squared. And here I have what is left is 2n plus 1 times 2n, and then this was the n squared there. Okay, now the limit as n goes to infinity here in the bottom, I have n squared, n cubed, n to the fourth, and this is just n squared. So as n goes to infinity, that is 0. We know that from prior art. And so by the ratio test, the series converges absolutely, and so it converges. Another example, this is example 4. Again, it's a good problem for you to practice. Determine if the following series is convergent or divergent. So this is the summation from n equal 1 to infinity of 9 to the n over minus 2 whole to the n plus 1 over n. Now this is not a geometric series. It's not a geometric series for two reasons. One of the reasons is you've got this n laying out here, which is not that. And another reason, although you only need one reason, another reason is that these exponents aren't the same. So anyway, we'll start computing it though. So L then is what we compute. This is the limit as n goes to infinity of, this is a n plus 1. So I'm putting n plus 1 everywhere. So I get 9 to the n plus 1 over minus 2 whole to the n plus 1 plus 1. That's n plus 2 over n plus 1. And then I divide it by a n. But that's the same thing as multiplying by the reciprocal. So I get minus 2 to the n plus 1 times n over 9 to the n. Now, this is 9 to the n plus 1 over 9 to the n, so that is just a 9. Here's n over n plus 1, and here I have minus 2 to the n plus 1 over n plus 2. That's just going to be a minus 2, but now I'm taking the absolute values before. Now I can pull out the 9 over 2. The absolute value took care of the minus sign, and this is the limit as n goes to infinity of n over n plus 1. Well, this is known to be 1, and so this is equal to 9 over 2. Now 9 over 2 is bigger than 1, so by the ratio test, this series is divergent. Now notice that if we didn't have the absolute values, we would have had L is equal to minus 9 over 2, which is less than 1, and that would have told us it's a convergent series. The wrong answer. Okay, so let's look at another example. And in both of these next examples, it turns out L is equal to 1, but there are things to be learned from there. Okay, so determine if the following series is convergent or divergent. You see it's an alternating series. This is a summation of n equals 0 to infinity, minus 1 whole to the n over n squared plus 1. Again, a good practice problem. Okay, so let's calculate L. And again, we're seeing how we crash and burn. So L is equal to, we change the n to n plus 1. Now notice that this is minus 1 to the n plus 1 all over n plus 1 whole squared plus 1. This is n squared plus 1 over minus 1 to the n. So whenever I look at the negatives, I see that I end up with minus 1 to the 1 power, which is going to be 1 when I do the absolute value. So that goes away. And then I have n plus 1 whole squared plus 1 over n squared plus 1. You may have to do a little bit of work on this, but the ratio of the leading coefficients here is still going to be 1, so this limit is equal to 1. But we recall from our theorem that means the test failed. So it's no good. So we have to do something else. But fortunately, we can do something else, because notice that 1 over n squared plus 1, the limit is equal to 0. And it is also decreasing. Bn plus 1 is bigger than Bn is bigger than Bn plus 1. So it decreases to 0. So what you see is we can apply the alternating series test to this and declare that this is convergent. And so another thing that you could have done is you could have taken the absolute value of this and compared it from a p-series test. And I guess this follows directly from the comparison test for the p-series with p equal 2, also if you were taking the absolute values of that. Here's another example. Determine the following series is convergent or divergent, and we're showing you what can happen with the ratio test. So here's the limit. So L is the limit as n goes to infinity. This is what happens if we put n plus 1 in. So this is n plus 3. That's n plus 1 plus 2, all over 2 times n plus 1 plus 7. And then this is a n, but I turn it upside down. So this is 2n plus 7 over n plus 2. So when I start looking at this, what I see is this is 2n squared if I expand it. This is 2n squared if I expand it. So this limit is going to be 1. The test fails. But what we could also do is look at, well, what's the limit of this thing, the terms, as it goes to 0? Well, this limit is equal to 1/2, and that's not equal to 0. So by the divergence test, we know that this series is divergent. Now we saw in the previous two examples, if we get L equal 1 from the ratio test, it can be either convergent or divergent. There's one thing that we should note about the ratio test before we move on to the next section. A lot of times, if you have a polynomial divided by a polynomial, we'll get L equal 1. And so you want to expect this to happen from time to time. Okay, let's close out the section with a proof of the ratio test. Again, here's a statement of the ratio test. So what we're going to do is we're going to prove these. There's the if part and there's the then part, and this is common to all of the if parts. Okay, so first we note, and we can assume without loss of generality, that the series starts at n equal 1. So we'll start out by assuming that L is less than 1 here, and we need to show that the summation of a sub n is absolutely convergent. Well, note, because L is less than 1, there's some number r such that r is between L and 1, and so we're going to pick some number r that does that. And since L is equal to this limit, we've chosen r such that this is less than that, and so there's some n such that for every n greater than L, we have this ratio is less than r. And that implies that this term is less than r times the previous term. And so when we start looking at this, then that says the absolute value of an plus 1 is less than ran. But then ran is less than or equal to, this is going to be r times an plus 1, and this less than r squared, r cubed, r to the fourth, and r to the k, all of like this. So you see the absolute value of each of these terms is less than r to the k times a sub n for all of these things that are bigger than that. Well, why is that important? Well, if we look at this series, then this is a series which is bigger than the series that this is a series that dominates the one we have. And so what we're able to do is look at this. Now this is a geometric series. There's the constant that is right there. And this is r to the k. And so we know this converges. And in fact, we know that this converges absolutely because r is between 0 and 1. So it's a geometric series. It converges absolutely. and this is less than this, so that says our original series also converges, so it's absolutely convergence. To summarize this, what you're doing is, whenever you have this being the case, eventually, for n large enough, this starts looking like a geometric series. And that will be the same thing that we'll see in the root test later. Now, we only did part of that, though. We said, well, what happens if L is bigger than 1? Well, if L is bigger than 1, you'll see that these are increasing. And because L is bigger than 1, there must be some n such that we will have that this is bigger than 1, because the limit is bigger than 1. And so that means that this is true, and that means it is an increasing sequence. However, if this is greater than that for all n, we know that the limit can't be 0 because the terms are getting larger and are guaranteed not to be negative. This means the limit as n goes to infinity of a sub n does not equal 0. Therefore, by the divergence test, the summation of a sub n is divergent. Finally, we need to show that when it's L equal 1, you could get any of the three possibilities. And when L is, if you did this, L would be 1 for this one. And we know this is absolutely convergent because this is a p series. This one is conditionally convergent because the alternating series test says this does converge, but does not converge absolutely, because that would have been the harmonic series. And the harmonic series at least is divergent. So all three of these examples would have L equal 1. And so that's what happens, and we would have to do something else. Now, time permitting, I hope to cover an optional topic called, actually it's an additional topic, it's not even officially an optional topic, called Rob's test, which sometimes works well when L equal 1. We'll see if we have time for that. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now, more than ever, take care of yourself and of each other. We are all in this together. May God bless you all.